Alright, so we're continuing in the minimum cost network flow problem section. That's section 8.5, and we're now talking about translating different network models into the minimum cost network flow problem model, or you could call it the framework as well. And so in this case we're looking at the shortest path, and so we have a starting node and an ending node, and we have some I guess you could call them costs or path lengths, right? And so the problem with the shortest path is to find the path, from 1 to 4 using the smallest sum, right? And so what will the considerations be to translate this? Well, these could be distances, right? And so for us, though, we're just going to call them costs. And so we'll be minimizing the cost again. So costs are the values on the edges. And then we have to decide how to make this into a supply-demand problem, right, or a transportation problem. And so the idea is that the first node, the starting node, is going to be the supply node. So first node is the supply node. And so what will we put as our B1? Do you remember? I think we did this before. 1. And so that means that in order for this to be balanced, then the last node has a demand of 1 as well, right? So that would be, so B4 is going to be -1. So B1 is 1, B4 is -1. And then for 2 and 3, what do you suppose we'll do? Yeah, those are transshipment nodes, right? So we set those to, the BIs are equal to 0 in those cases. Good. And so now we're ready to write down our minimization problem. So we're going to minimize. Let's see, 212, or 2x12. That's not an I. 212 plus 4x13 plus x23 plus 2x24 and then plus x34. Good. And so node 1, what are we going to put for our flow, conservation of flow? We have our two outputs, x12 and x13. Those have been very similar, right? And so that's going to be equal to 1. And then for node 2, what do we have? We have an input. 1, 2 is an input, so that's going to be a minus x12. And then the two outputs are 2, 3, and 2, 4. And so that will be equal to what? Did you say 0? Good. And then for node 3, we have two inputs and one output. So 1, 3 is going to be negative. What's the other one? 2, 3 is going to be negative. And what's going to be positive? 3, 4. And that's a transshipment node, so that's 0. And then our last node is node 4, and so that's going to be all negative values, right? 2, 4, and 3, 4. And then we have a negative 1 demand as well. Good. So there it is with xij equal, or oops, xij greater than or equal to 0. Good. And so there's the shortest path problem as a minimum cost network flow problem. Good. I'm going to pause now and set up the maximum flow problem. Alright, so here's the maximum flow problem. And in this case, remember that the numbers appearing on the edges are what? They are not costs anymore, right? They are capacities. Yeah. So in this case, we have to figure out what our cost should be. And so let's see, how are we going to do that? What should be the costs? So that's the thing that we're going to maximize or minimize. And that should be the sum of the nodes out of S, right? That's how we compute our the value of the flow. And so, by the way, I think the general case would say that it would be the sum of the outflow from node S minus the inflow to S. But if we have a true source, right, then we shouldn't have an input to the source. I guess we could have an input to the source if, our book gives us a new edge here, but normally we don't have that. And so in this case, we're not going to have an input to the source. And so the way we're going to do this is we're going to create a new variable. And the variable that we'll create will be V. And so we will say let V be the value of the flow. Then what we're doing is taking B corresponding to the source is going to be V, and the B value corresponding to the terminal value is going to be minus V. Okay, and so we're also going to be then maximizing V. So we're going to maximize V such that now we go in and we do our node conservation, or our flow, the conservation of flow on each node, right? So let's see, before we do that, how many variables do we have here? We've got 7, right? So let's just keep those straight. So I'm going to pause here maybe and just write these down so you don't have to watch me. Okay, so here are our equations. So for example, let's just pick one of these. In this case, this should be node 2. So in node 2, right, we see one incoming here, one incoming there, one outgoing there. Okay, so the incoming 1, 2 is negative. Oops, sorry, I think I said that wrong. The outflow is positive, inflow is negative, right? So outflow here is from 2 to 3, and so for node 2, oh, wait a minute, this is node 1 that I'm pointing at. So this would be node 1, right? So I'm looking at the wrong node. So node 1 is right here. Let me get rid of those. Okay, so then for node 1, the inflow is negative, outflow is positive. So 1, 2 is positive, 1t is positive, and then S1 is negative. Good. And then set that equal to 0. By the way, the V, normally you wouldn't want to have a variable name on the right hand side, so you could always just move this over to the other side, make it equal to 0 when you're actually writing this into a computer program. Then you'd have your right hand side all constant, which is what some programs want you to have. Good, but wait, we're not finished yet, because next we have to make sure that we are maintaining our capacities, right? So therefore, we also have XS1 being between 0 and 2, XS2 being between 0 and 8, XS3 being between 0 and 3. You see what's happening here? X12 is between 0 and 7, I think. Where is the 7? 1, 2? Right here. And then X1t is between 0 and 2. And then X23 is between 0 and 2. Okay. This is probably not entertaining anymore. Okay, just one more. We'll just finish it up. 3t is between 0 and 5. Good. That's it. We're finished. This has been how to convert the maximum flow into the minimum cost network flow problem. Of course, you might be saying, well, it's not a minimum, it's a maximum. Well, that's easy though. To change that, you would just say minimize minus V. Good, and then we're done. Now it is a minimum cost. All right. Yes, so that finishes us up for section 8.5, and so the next video will be section 8.6, which talks about minimum spanning tree problems.